Hello everybody, I am Peter Klapper from the School of Biosciences at the University of Kent, and I want to show you in a practical example how we can actually find the enzyme parameters of an enzyme catalyzed reaction with an Eadie Hofstee plot. So first of all, let's assume that you are a research scientist and you study a new enzyme and you want to characterize this enzyme. So what you do is you measure the velocity of the enzyme catalyzed reactions at different substrate concentrations, and you actually measure your data. Here you have your substrate concentrations and you measure the corresponding initial velocities, the initial rates. And in order to characterize the enzyme a little bit more, you need to determine Vmax. That basically tells you how the enzyme behaves at very high substrate concentration. So towards this end here, you want to determine Km. That gives you an idea of the affinity of the enzyme for its substrate concentration. And you want to find out Vmax over Km. This parameter actually gives you an idea how the enzyme behaves at very low substrate concentration, so at this spectrum here. So how can we do that? Well, before we get going, we always want to find out what we actually should expect. And therefore, it's always a good idea to make a guesstimate what we should expect. So how are we going to do that? Well, the easiest way is to say, right, let's look at our velocity, and we are looking for Vmax. We know Vmax is the maximum speed at which this enzyme reaction can happen. So Vmax certainly must be larger than this value here, than this 40.5. So perhaps, well, maybe this Vmax might be around, say, 45. So let's assume that this could be a valid guesstimate for our Vmax. What we then can do is we can say, okay, Km is actually defined as the value. So Km is the substrate concentration that results in half of Vmax. So in order to find Km, what we need to do is we need to take our Vmax, our guesstimate here, take half of it. So half of 45 millimolar per minute, that would be 22.5 millimolar. That's quite convenient that we've got something like that here. And we need to find the corresponding substrate concentration. And we find that the corresponding substrate concentration would be 10 millimolar. So we can assume that 10 millimolar is the substrate concentration that gives us half of Vmax. That means our Km would be around 10 millimolar. And once we've got that, we've got Vmax and we've got Km, we can very easily guesstimate Vmax over Km, and that would be 45 divided by 10, so that would be 4.5 millimolar per minute and millimolar. I'm running out of space here. Okay, so this is our guesstimate, and let's see how we can do that more accurately with a good graph. So here again are the data for our guesstimates, just to make sure that we have these data. And now we need to calculate our data, actually, and prepare them for an Eadie Hofstee plot. So what do? We have our substrate here, we have our initial velocity, our rate here, that's the corresponding one. And remember, for Eadie Hofstee plot, we need to calculate rate divided by the substrate concentration. So all we need to do is really calculate this value, 10.4 divided by 3. So 10.4 divided by 3, and that gives 3.47. So that was our first calculation. We then calculate 14.5 divided by 5. So I've written that here, 14.5 divided by 5 gives us 2.9, and so on and so forth. So we basically calculate the initial velocities divided by the corresponding substrate concentrations, and we get a nice list of these data here. And now we are more or less ready to plot. So here again are our data. Here is the initial velocity that we used, and here we've got velocity divided by the substrate concentration. We have to make sure that we do our plot correctly. So what we do, we plot on the x-axis, we plot velocity over substrate. So here, that's the data that we just calculated, velocity over substrate, and we have to be mindful of the units. So the velocity is given in millimolar per minute and divided by the substrate concentration, again in millimolar. Of course, we could, without any problems, we could cancel the millimolar, and we would get, for velocity divided by substrate, we would get the unit of millimolar, per minute, sorry. Anyway, let me quickly go back to that. And so we plot velocity over substrate concentration, and we plot on the y-axis, we plot velocity of the reaction. And again, we have to be mindful of the units of this, so millimolar per minute. And now all we need to do is plot our data. I've done that here. So, for example, what we have here is basically we have velocity over substrate, so 0.45, and the corresponding initial velocity would be this point here, so 0.45, that gives me 0.45, gives me this point here, and I plot all the data. And obviously they are very nicely lined up, so all we need to do is draw a straight line through these data. So we get this, and they are fairly reasonably on a straight line. And what we then can do in order to find out our Vmax and the parameters is we can basically extend this line, and we get these points here, we get these intersects with the y and x-axis. And what we do know is that because we've got the velocity here on the y-axis, this intercept here, that represents actually our Vmax. So this point, and we can read this, that is probably around 44.5. We can read this very nicely from the graph. Likewise, we can look at this intercept here, and because it is on the velocity over substrate axis, we know that this intercept here must be our Vmax over Km. And from the gradient, we can very easily determine the gradient here. We know that the gradient must be minus, so it goes down, minus Km. We know that Km is always positive, but the gradient here, obviously, because it goes down, would be negative. So if we read these numbers, what we get here, Vmax is around 44.5. Very important, the unit millimolar per minute. For the gradient, we can determine this versus this, and we will find that our Km equals 10 millimolar. And for the Vmax over Km, we would get, well, that is 4.45. It's not exactly 4.5, so 4.45. And the units for that would be millimolar per minute and millimolar. And I'm running out of space here again. So you see, we could very easily determine Vmax over Km. So Vmax, this point here, Vmax over Km, this point here, and our gradient of Km. So let's see how this pans with our guesstimate that we had previously. So we found that our actual numbers from the graph are Vmax equals 44.5 millimolar per minute, and we estimated it to be 45 millimolar per minute. So that's in fairly good agreement. Km, we said, is 10 millimolar. And our guesstimate again was 10 millimolar, so we were more or less spot on. And likewise with the Vmax over Km, we got a fairly good idea from our guesstimate. And because with the guesstimate, we did not use any fancy calculations or any graphs, it was just looking by visual inspection. What could it be? We got a very good match with the values that we got from the graph, and therefore we can be fairly confident actually that our data are correct. And in fact, when I designed these data that I used here, I used Vmax of 45 millimolar per minute and a Km of 10 millimolar. So I think we were really very good with our guesstimate, and this was confirmed by the graph. And the important message is that an Eadie Hofstee plot really gives a very nice and convenient way to determine the enzyme parameters, but it's always a good idea to guesstimate roughly the parameters before we do the plot. I hope you found this helpful, and thank you for watching.